From previous discussions, you should know that the area under the curve for any probability distribution equals 1 or 100%. The above statement is true whether we're discussing continuous distributions, such as the normal distribution, which have a probability density curve associated with them, or we're discussing discrete distributions, which have a histogram associated with them. Today's video introduces the concept of a binomial probability experiment, as well as the associated key discrete random variable probability distribution known as a binomial distribution. Please note, the reason that we're emphasizing the normal and binomial distributions in this course is because they are at the heart of the inferential statistics techniques we will look at for the remainder of the course. So let's consider the following scenario. Suppose we flip a fair coin 3 times and we want to know the probability of flipping 2 heads out of the 3 coin flips. Below I've shown what that would look like using probability notation. So in that scenario, the following conditions are met. Firstly, we are performing a fixed number of trials, or in this case, coin flips, in which we are doing 3 trials. Secondly, each trial or coin flip is independent of the others. That is, a flip of the coin doesn't influence the probabilities associated with subsequent coin flips. Thirdly, each trial or coin flip outcome can be categorized as a success or a failure. In this case, flipping a head would be considered a success. Fourth and lastly, the probability of success for each trial or coin flip remains constant. That is, the probability remains at 1/2, where P represents the probability of success for each trial or coin flip. Therefore, the scenario that we've been looking at is an example of what we call a binomial experiment because it satisfies the 4 conditions we just discussed. As a result, we will find that the so-called binomial distribution, which is a special discrete random variable distribution, can be used to solve the problem. Before we get to the binomial distribution, though, let's take a look at solving our problem with some basic probability techniques from Chapter 3. So we know the possible outcomes for our experiment are the following, and here I've shown the sample space with all the possible outcomes for flipping a fair coin 3 times. For any of those 8 given outcomes, let's say heads, 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 we know that the probability is 1 out of 8. Because the probability of flipping 3 heads is equal to the product of the probability of flipping just a single heads times itself 3 times, because they're independent outcomes or independent events. So that would be 1/2 to the 3rd power, and that would be 1/8. And that would be true. That probability would be the same for all 8 of these outcomes that we have listed in the sample space. Therefore, we can construct a probability distribution table as follows. Notice on the far left column I have listed the event of the number of heads that are possible out of 3 coin flips. The middle column lists the outcomes from our sample space that correspond to each of the events for the number of heads. And then the probability of each of those events, 0, 1, 2, or 3, is given on the right, and that's found by just taking the number of outcomes for that event and dividing by the total number of outcomes, which is 8. Notice that the probability of flipping 2 heads out of 3 coin flips, which is what we started with as our problem, is 3 out of 8, or 375 thousandths. Here we take a look at a picture of that distribution. So the probability distribution is shown with the number of heads, number of successes on the bottom axis. The vertical axis gives us the probability measure for each of those events. So the height of each rectangle corresponds to the probability of getting that particular number of heads. And we know that the area inside all 4 rectangles, if we add them together, will equal 1 or 100%, where we're assuming that the base of each rectangle has a measure of 1, since the area of a rectangle is base times height. The last thing I want to point out about the distribution is that it's symmetric, which means it's symmetric about the center or the mean value, which we see in this case the mean value would have been calculated as 1.5. That would be the expected value for this particular scenario of flipping a coin 3 times. And the standard deviation is 866 thousandths. Now that we've finished the problem of figuring out the probability of flipping 2 heads out of 3 coin flips, we ask the following question. Suppose that we change our scenario and we want to know the probability of flipping 2 heads out of 20 coin flips. This is a much more difficult problem to solve using basic probability principles. Wouldn't it be nice if we had some other method of finding probabilities for a binomial experiment problem? And it turns out that there is a formula for finding probabilities of binomial experiment outcomes. And if you're interested in seeing that formula, you can look in section 4.3 of our textbook. However, rather than using a formula, we will instead use technology to find such probabilities. Before we look at how to use technology to solve the problem that we've been talking about, let's take a look at some notation. Binomial probabilities are expressed using the following notation, which I now have shown on the screen. So we have capital P for probability, which is the same as we've seen in Chapter 3. Then in the parentheses, we have a capital X representing the event we're looking for, and then some condition, an equal sign, less than symbol, some sort of mathematical symbol for the condition. Then K is the number of successes that we are interested in this case. Then we have a vertical bar, which from our work in conditional probability, we know that that stands for given that. So given that n equals a certain number of trials and the probability of success P equals some value. So here's the notation for the scenario that we have been looking at, flipping 2 heads out of 3 coin flips. We would have capital P, parentheses, the event of flipping 2 heads, so X equals 2, given that the number of trials, that is coin flips, equals 3, and the probability of a single head being flipped is 1/2. So for 3 flips of a fair coin, the probability of flipping 2 heads is given by the notation shown, and we are now going to find that probability using our guru. So within our guru, we start by left-clicking on probability simulation, go to the probability selection, left-click on that, go to probability calculator. Notice that this time we are not going to go to continuous for our probability calculator because, of course, that is for continuous random variable distributions like the normal distribution. We now want to go ahead and select discrete because the binomial distribution is a discrete random variable distribution. So this dialog box should be fairly familiar to you. It's very similar to the one we had for continuous distributions. I don't need to worry about filling in the name for calculation. I am again looking for values of a random variable going to calculate a probability. In this case, the distribution is binomial, comes up by default. There are other distributions, other discrete random variable distributions you could choose, but we want binomial. The number of trials in this case, we are talking about 3 coin flips, so the number of trials is 3. The probability of any one coin flip coming up as heads is 1/2 or 0.5. And I'm looking for the probability of getting exactly equal to 2 heads out of the 3 coin flips. So I select the equal from the drop-down menu and fill in 2. And now let's preview what our value is. And we see in the dialog box that the answer is a probability of 375 thousandths for flipping 2 heads out of 3 coin flips, which is exactly what we got when we used basic probability principles just a few minutes ago. So in conclusion, after having used our guru, we would now write our final answer for the probability of getting exactly 2 heads out of 3 coin flips using the notation shown, and our answer is 375 thousandths. So continuing with our scenario of flipping a fair coin 3 times. For our second example, let's consider the following. For 3 flips of a fair coin, the probability of flipping at least 1 head is given by the notation shown on the slide. In other words, I want the probability that X is greater than or equal to 1, which we will now go ahead and find using our guru. So within our guru, in the discrete distributions probability calculator dialog box, all of the settings remain the same except for the fact that we now want to use the drop-down selection for the random variable to be above. Now, above means greater than or equal to a random variable value. And in this case, we want greater than or equal to 1. And so when we click on the preview for that, we see that the probability of getting one or more, that is at least one head out of 3 coin flips, is 875 thousandths. So, having used our guru, we now know that the probability of getting at least one heads is 875 thousandths. It's worth noting that if we went back to our table that we constructed using basic probability principles and we added up the probabilities in the table for 1, 2, and 3 heads, we would find that that probability would be 875 thousandths. Or we could use the complement rule and simply take 1 minus the probability of getting 0 heads, which is 1/8, and get the same exact answer. So let's look at one last example with the 3 flips of a fair coin that we've been talking about. We now want to find the probability of flipping no more than 1 head, that is either 0 heads or 1 heads. And I've shown on the slide how that would be represented notationally. So the probability that x is less than or equal to 1, given that we have 3 flips of the coin, 3 trials, and the probability of each head is 1/2. Let's see how we would find that probability using our guru. So now within the R Guru Discrete Distributions Probability Calculator dialog box, everything's still the same. We're still dealing with 3 flips of the coin, 3 trials. Probability of each coin flip coming up heads is 1/2. But now in the dialog box drop-down menu, we are looking for below. That means less than or equal to the value we now put in the box, which in this case I'm going to put 1. So I want less than or equal to 1 coin flip coming up heads. We preview the answer for that and we see that the answer for that happening is 1/2 or 5/10. So having shown how to use our guru to find the probability shown on the screen, we now know that the probability of getting no more than 1 head out of 3 coin flips is 5/10. Notice that we could have gone ahead and used our table that we constructed at the beginning of this lecture, and we would have gotten exactly the same answer by adding the probability for getting 0 heads plus the probability of getting 1 head, which would be 1/8 plus 3/8. That would have given us 4/8 or 5/10, which is again 1/2. So let's summarize what we've seen so far. When we can identify that we have a binomial experiment, that is, that the 4 conditions or requirements are met that we saw that defined a binomial experiment, then we can use our guru to calculate probabilities. Let's take a look at one more problem, that difficult problem that I asked a few slides ago. What's the probability of flipping 2 heads out of 20 coin flips of a fair coin? In other words, we want the probability that x is equal to 2, given that the number of trials is 20, and the probability of flipping a single heads is still 1/2. Let's go take a look at what that value would be using our guru. So within our guru, we're still working in the Discrete Distributions Probability Calculator dialog box. So this time, the number of trials that we're looking at is 20 coin flips. Probability of success is still 1/2, and we are looking for the probability that we get exactly 2 heads out of 20 coin flips. Let's see what we get in this case. A very small number. Now again, keep in mind that all probability values in this course are to be rounded to 4 decimal places. So to 4 decimal places, that value would be 2 10,000ths. As we begin to close out our lecture, there are 2 final items that I need to mention. First, the mean and standard deviation for a binomial distribution are given by the formulas below. Secondly, the shape of the binomial distribution is determined by the values of n, the number of trials, and p, the probability of a single trial's success. I'm going to go to the Art of Stat website to quickly demonstrate what I mean by that. So at the Art of Stats website, you can see that I've set it up for the case we've been looking at throughout this lecture. That is the number of trials being 3 for 3 flips of a coin, probability of success of a single coin flip being 1/2, and we see the symmetric probability distribution that we have been dealing with all lecture. Notice that if I move the cursor around, we get extra information, the probability of each of those events, 2 heads, 1 head, 0 heads, etc. But what I want to show you now is when p is 1/2, we get a symmetric distribution. What if I make p extremely small? So let's say 0.1. Notice what happens is the distribution becomes a right-skewed distribution as a tail to the right. And the same thing would happen if I make the probability 0.9, then it becomes a left-skewed distribution, which makes sense because if the probability of a head now is 9/10, in other words, an unfair coin, that means I'm more likely to get more heads out of the 3 coin flips. Now let's see what happens if I change to 20 coin flips. We still have a very left-skewed distribution with the probability of getting heads being higher for higher numbers of heads out of 20 coin flips. Again, if I change my distribution's probability of success to 0.5, we get a symmetric distribution. And if I change it to 0.1, we can see that I now have a right-skewed distribution in that case. So the increase in the value of the number of trials gives me, of course, a wider distribution for the binomial distribution, and changing the value of p changes the skewedness of the distribution. If it's a small value of p, it's a right-skewed distribution. If it's a large value of p, it's a left-skewed distribution. So that's how n and p affect the shape of a binomial distribution.